Yo! So, we officially have a week until AP test. Yikes. Let's see what we can do with this video. Just like with the last couple of videos, you had one that was conceptually based in derivatives and then applications. We had the one that was conceptually based in integrals. Now we're going to get a lot more application. So this is going to be a lot of math. Stay with me. Also, I sent a bunch of stuff out yesterday talking about the AP test, the mock AP test that you can do, the PDF thing that gave you all of that information. Make sure you're checking all that stuff out before Monday, please. Don't wait till the last minute to do it. And I know who you are because you keep emailing me about your assignments that you wait till the last minute to do. But go check all that stuff out so that come Tuesday, we're ready to roll and you guys can show what you know. From there, I want to start going into some mock AP style things. I have a Princeton review book and a couple other resources that have excellent AP style questions. I'm going to be going through specific applications of integrals and how they relate to what you might see on the AP test. Next, I'm going to talk about some volume, some rotational volume, and some cross-sectional volume, including some areas in between two curves. And then the last thing I want to focus on is, I have no idea and I forgot what I was going to say. Differential equations. I finally remembered it. So we'll talk about those four main concepts and I'll give you key pointers as we're going through there. So here we go with integration techniques. You basically have 5 major things that you can do when it comes to integrating, as far as we know in Calculus BC. The first one you need to focus on is any algebraic manipulation. Remember, the only thing that we can just look at and integrate are those things that are on the right-hand side of our yellow sheet. Anything that I can use an identity and say this is this, like 1 over x is equal to natural log. Or using your reverse power rule. And remember, the only time I can use my reverse power rule is if I have a variable raised to a singular exponent. Other than that, I can never use my reverse power rule. So look at this example.
So the first technique is manipulation, if I can manipulate it algebraically. If I see something like this, I notice, okay, the top could be factored, but that's not going to help me. The bottom is only a singular term. When I only have one term on the bottom, I can divide everything by that term. If there are 2 terms, can't do that. So I can rearrange this to be the integral of x squared over x to the 1/2 power is going to be x to the 3/2 power. X to the 1 over x to the 1/2 is going to be x to the 1/2 power, and then 2 divided by this, I just move that to the top. So x to the negative 1/2 power. I'm just dividing each term by x to the 1/2, which represents this. Now I can integrate each term by themselves because they're each variables raised to an exponent power. So the first one is going to be x to the 5/2 divided by 5/2. The next one is going to be x to the 3/2 divided by 3/2. This negative 2 is a coefficient. It sits up front. Then I increase the power, x to the 1/2 divided by 1/2. I have a plus c at the end, and if I really want to, I can clean this up. Dividing by a fraction, I can flip it and multiply by its reciprocal. So this is going to be 2/5 x to the 5/2 plus 2/3 x to the 3/2. Flip this 2, this will become negative 4 x to the 1/2 plus c.
The second big integration technique is called U sub. And the big key for U sub is if I have its function and I have its derivative. If I have both of those things at the exact same time, the function and the derivative in one integral, then I can do something called U sub, where I can cancel out the function with its derivative and I can go from there.
The next one is U substitution. And I can use U substitution when I can take the derivative of one part and cancel that with the other part. In this case, I have something with an x squared. The derivative of an x squared will be an x component, and I'm thinking that will cancel out there. So I can U sub the entire bottom, what's on the inside, don't take the square root, 4 plus x squared. Therefore, du will be equal to derivative of 4 is 0. Derivative of x squared is 2x times dx. Divide by 2x. So du over 2x is equal to dx. So I can replace this, and I can replace the dx component right there. Replacing all of that, I now have the integral, which is x over square root u now, times du over 2x. The x components will cancel like I wanted them to, and this 2 that's in the denominator can bounce up front. So this becomes 1/2 the integral. U on the bottom becomes u to the negative 1/2. Remember, I cannot integrate something that isn't just a singular variable raised to an exponent power. I can apply my reverse power rule now. This is 1/2 times u to the positive 1/2 divided by 1/2 plus c. Let me flip this and multiply. If I multiply by 2, these will cancel. So I'm left with u to the 1/2. I have to remember to replace the u, so I can plug in what I substituted in the beginning. So this is 4 plus x squared to the 1/2 plus c.
The next big category is using algebra techniques to go a little bit further. We use long division and completing the square. I'm going to run through these examples really quick because it's something you should remember, but we still need to remind you of it. So check this out.
The next one is long division. I'm going to use long division when I have an improper fraction where the top of some polynomial is bigger than the bottom. And this is an Algebra 2 concept where I can divide that bottom part by everything that's in there and go from there. So everything that's up top goes inside, everything that was underneath goes out, and I can go through my long division. What times x gets x cubed? That's going to be an x squared. So this is going to be x cubed minus 2x squared. I subtract all of that. This adds, so I get negative x squared. Drop down the 4x, so plus 4x. Then I repeat the process. What times x gets negative x squared? That's going to be a negative x. Repeat the process. Negative x squared, positive 2x. Subtract all of that. These cancel again. This is going to give me a positive 2x. Subtracting 4 minus 2x. Bring the negative 1 down. And then finally I get the last one. What times x gets 2x? That's going to be a positive 2. 2x minus 4. Subtract all of that. These cancel. I'm left with a 3 as a remainder. So the integral that I'm now integrating is x squared minus x plus 2, and then a remainder portion, which is 3, over what I was dividing by, x minus 2. Now all of these are pretty simple to integrate. Integral of this is going to be 1/3 x cubed. Integral of this, 1/2 x squared plus 2x. For this one at the end, you need a very small u sub. U is going to be equal to x minus 2. So du is equal to dx. So it just becomes the integral of 1 over u, or 3 over u, which is natural log. So plus 3 ln of x minus 2. And then a plus c at the end. You can also lump in some completing the square. So if I have something that looks like a perfect square on bottom, I can turn it into a perfect square, hopefully use some trig identity to integrate it. So in this case, I'm going to have the integral of 1 over x squared plus 2x plus something that's going to make it a perfect square at the end. But if I do that, I also have to subtract that something so I don't change the value. Well, to do that, I take the middle term, I divide it by 2. 2 divided by 2 is 1. I square whatever that is. 1 squared is 1. So that makes 1 and 1. So I can factor this. This will then become what times what gets x squared? That's an x. What times what gets 1? That's 1. So the perfect square that I make is x plus 1 squared, and then 5 minus 1, I get a 4. And I could rewrite that 4 as 2 squared. And if I have the integral of something squared plus something squared, remember that is going to be an arctangent. Arctangent, remember, will be 1 over a, arctangent of the variable divided by a. So this is going to be 1 over 2 arctangent of x plus 1 divided by 2 plus c.
The next big one, and the one that most of you don't really like that much, is integration by parts. Remember, integration by parts is when I have two things that are multiplied by each other. So say an x squared and an e to the x, or 2x and a sine of x. Speaking of that, let's look at that example.
Integration by parts is for the multiplying thing. Now I have a 2 up front that can just go all the way up front. So this is 2 integral x sine of 3x dx. In this case, remember, I need to pick a u and a dv. The u I have to be able to take the derivative of. The dv I have to be able to integrate. In this case, I'm going to choose my u as my singular x, and I'm going to use my dv as my sine of 3x dx. If I take the derivative of x, I get dx. If I integrate sine with this 3x in there, I'm going to need to do very small use. Most of you can do this in your head by this point, but this is going to be negative 1/3 cosine of 3x. Everything froze, everyone panicked. Let's pick back up where I left off. I integrated sine of x to get negative 1/3 cosine of 3x. Very small u sub here, where u is equal to 3x, so du was equal to 3 dx. Divide by that 3, so du over 3 is equal to dx. Then from here, all I have to do is put the parts together. So u and v, negative 1/3 x cosine of 3x, then minus the integral of v times du. V is this portion, du is dx. So I can pull out this 1/3. This becomes positive 1/3 integral of cosine of 3x dx. Again, another very simple u sub where u is equal to 3x, and I can go from there. Integral of cosine is going to be sine. There's going to be another 1/3, so this turns into 1/9 sine of 3x plus c. So all told, the full answer is negative 1/3 x cosine 3x plus 1/9 sine 3x plus c.
And the last big integration technique that will show up on this AP test is partial fraction decomposition. That's where we take something that is an improper fraction and we break it apart into two different parts. We can break it up into one fraction here and one fraction there, and then we can integrate those fractions using some sort of u sub or some sort of identity. So check out this example.
The last one in big concept is partial fractions. I can integrate this by breaking it up into two components. The bottom factors into two linear factors. It factors into x minus 2 and x minus 1. Now I want this to be equal to some fraction containing the x minus 2 part and some fraction containing the x minus 1 part. To do this, I'm going to need to get a common denominator. So what does this denominator not have that the original one does? It's missing an x minus 1. So I'm going to multiply top by x minus 1 and bottom by x minus 1. The second one is missing an x minus 2 component. So I'm going to multiply by x minus 2 and x minus 2. So all told, if this is going to be true, this is 1 over x minus 2, x minus 1 is going to be equal to a x minus 1 over that same now common denominator, x minus 2, x minus 1, plus b x minus 2, x minus 2, x minus 1. Now if the bottoms are all the same, I don't need to worry about them. I can only look at the top and try and figure out what my a and b are. Well, to do that, let's do some educated guessing. I'm going to plug an x in as 1. So if I do that, I get 1 is equal to a 1 minus 1 plus b 1 minus 2. 1 minus 1 is 0, it cancels out, so I get 1 is equal to negative b. So b is equal to 1. Do the same thing in educated guess. I'm going to choose a 2. So x is equal to 2. If I plug that in, I get 1 is equal to a 2 minus 1 plus b 2 minus 2. The 2's cancel. I'm left with 1 is equal to a. So this integral just now turned into 1 over x minus 2 dx plus this integral negative 1 over x minus 1 dx. I broke this original fraction that could be factored into partial fractions, two separate fractions based off of their linear components, which allowed me to integrate them. This can do a very easy u sub. U is equal to x minus 2, so du is equal to dx. Same thing over here. U is equal to x minus 1, so du is equal to dx. If I get that, I can do 1 over u, which hopefully you remember by now is natural logs. So this is going to be ln of x minus 2 minus ln of x minus 1. Tag a plus c on it, and you are done.
Like 3 words of word. There you go. That's basically like 3 weeks worth of material summarized in basically 6 examples. So go back and look at those if you need to, but those are our main techniques of integration that you would be expected to do on an AP test. Yes. And what will likely be one of the biggest components on the AP test is using integrals as some sort of accumulation or to find mins and maxes. Now with this setup, the first fundamental theorem and the second fundamental theorem are absolutely imperative. You have to know those and know what they are saying. Remember, the first fundamental theorem relates a derivative to its original function. So if you're trying to go from a derivative to a function, likely you're going to need to use that. But the second fundamental theorem incorporates derivatives and integrals. Anytime you have derivatives and integrals together, remember they cancel each other out, and you can talk through the relationship once you find it there. So let's check out these examples.
Alright, so here's an example of when I can use the integral as far as accumulation and to find mins and maxes, a concept that will likely be very important on this test. If you need to, pause, get yourself familiar with what's going on here, because I'm just going to jump right in. First one is I want to find g of 2 and g of negative 2. Well, that's just using function notation because I have g of x and I want to find g of 2. So everywhere I see a 2 in my equation, I'm just going to plug in, or everywhere I see an x, I'm going to plug in a 2. This represents the integral from 0 to 2 of f of t. Well, given that this is f of t, or the function f, I can just integrate and find the area underneath this curve. So from 0 to 2 represents this triangle that has a base of 2 and a height of 1. So that will be 1/2 base times height, which will be 1. If I want to find g of negative 2, same idea. I plug in 0 and negative 2, f of t dt. Now there's something weird with this one because the bounds are reversed. I should be going from the smaller to the bigger. So I need to reverse these bounds by putting a negative in front of it and flipping them. And then that allows me to go normally. I'm finding the area underneath the curve from -2 all the way to 0. That's a quarter of this circle. The radius of this circle is 2. So the full thing would be pi r squared, so 2 squared times pi. But because I want a quarter of it, it's only going to be a fourth. So this is equal to pi. Now here's where my second fundamental theorem comes in for part B. Part B, I want to find the derivative of g at 1, g prime of 1. So I'm going to need to take the derivative of whatever is over here and then plug in 1. Notice how I'm not plugging 1 while I'm taking the derivative. In other words, you wouldn't be able to see that, hey, I'm supposed to cancel these out. This is a second fundamental theorem where the derivative and the integral cancel. Whatever is up here bounces in. And if there's a derivative of it, if it's a function, I would need to do that at the end. But in this case, I find that g prime of 1 is just be f of x. So at 1, it is f of 1. So I have to find the f value at 1. Well, if I go to my graph, this is the function f. So I go to 1, the value is -2. So g prime of 1 is the same thing as f of 1, which is -2. Part C is asking for the inflection point of g. I know the only thing that tells me inflection points would be the second derivative. I have the first derivative. The first derivative is equal to f. So if I take another derivative, the second derivative will be equal to f prime. G of x is equal to the integral. G prime is equal to the function. G double prime is equal to the derivative. So I want to know where the derivative is equal to 0 and changes signs so I can talk about g prime. Well, the places where the derivative is equal to 0, there is one right here. There's a sharp turn right here. There's a sharp turn right here. And there's a sharp turn right here. But remember, I have to change signs as well. The derivative up until this point is positive, positive, and then it changes to negative, negative. So at -2, I have an inflection point. As I'm going here, my derivative is negative and stays negative. So even though this derivative is undefined at this point, I don't have a sign change, so it's not a point of inflection. Here I have a derivative that is negative and positive. So the derivative of f, which is really g double prime, is undefined here, and it changes signs. I have another point of inflection here. Here I go positive, but then I have 0. I'm not changing signs because 0 doesn't have a sign. There is no concavity at this. So you can't say it changes concavity if there is no concavity. So the places where I have points of inflection are at -2 and at 1. Remember how to justify this. X equals -2 and x equals 1 are points of inflection. You are talking about g double prime. So g double prime is equal to 0 when it's at -2, and g double prime is undefined when it's at 1 because it was a sharp turn, and g double prime changes signs. That's the full justification, sings LOL, of why I have a point of inflection at those two places. And the last part of this is asking us to find at what value of x is g at a minimum. Well, if I'm going to talk about g, that means I have to be looking at the derivative of it. And remember, we've already found that g prime of x, or g prime of t, is equal to f of x. That's what we found by using the second fundamental theorem to evaluate it. So, if I want to find where the derivative of g is going undefined or equal to 0, I have to look at f to see where that is undefined or 0. And there are 3 places on our graph where the function is at 0. Right here it's at 0, right here it's at 0, and right here it's at 0. So then I have to look at the signs, and I'm looking for where it's finding a minimum. So right here, it is starting at 0, and it's positive. It's above the x-axis, meaning that my derivative is positive. So I'm starting at a point and increasing away from it. So that point is a minimum. So at x equals -4, I have a minimum. See if there's anywhere else. Here, I go from positive to negative above the x-axis, below the x-axis. And remember, we're thinking that this is really now g prime. So the derivative is positive, negative. That means it's increasing, decreasing. This will be a maximum. And then finally I get to here. I'm going from decreasing to increasing. That means that at equal to 2, I also have a minimum. Now, I need to figure out which one of these values is truly the minimum. If it says the absolute minimum, I go from there. Now, because of how this one is worded, I think you would be safe to stop right here and say, great, where is it achieving a minimum? This. But, because it's saying a minimum or the minimum, you want to be very specific. AP test will definitely clarify exactly what they want to do. For this, my document camera stopped working. I'm about ready to destroy it, but that's okay. So, what you missed when I was just talking and didn't realize that it was still going, and if I can record, there we go. Let me start this over again. My document camera decided to have a mind of its own again, and then Mr. Beanster got very angry and yelled at it. So, now it's working. So what you missed is if I want to figure out which one is the actual minimum and the actual maximum, I have to look at the values of g. I can plug in 2, I can plug in -4, and I want to see which one is actually lower. Now one of these we have actually already done. We've done the 2, and I made a mistake. I left out the negative when I did this calculation. This should have been -1 because it was below the x-axis, and this one should have had a -pi because it was going backwards. So if I wanted to find from -4 to 0, well, that would just double this value because it's the other half of the circle. So this would be -2 pi, and this would be -1. So in this case, the value at -4 is much lower than the value at 2. So the actual minimum is at x is equal to -4. Because when I plug in those values, I get -2 pi versus a -1. So the justification, because g prime of x is equal to 0 and g prime of x goes negative. It actually increases away from the endpoint. So it is an endpoint extrema. I ran off. Help!
We can also talk about velocity and acceleration and accumulation of things like that. We sort of discussed it in the third video that we talked about, but remember, if I'm given a rate, let's say grass per minute, if I want to figure out if I'm cutting the grass and I'm getting this much grass per minute, and I want to find the total amount of grass that is entering my mower, I can integrate whatever rate I have, and that'll give me the total amount. Just be careful. Remember, anything above the x-axis is positive. Anything below the x-axis is negative. So make sure that if you're looking for total amount or total distance traveled or whatever it's asking you for, that you're looking for the correct thing given the positive and negative and conceptually knowing what that represents.
Now here would be an awesome problem for you to try that incorporates all of these things. I'm not going to do it. I'm just going to leave it up and you can pause it on the screen and try it. You have a bunch of trains. This is the velocity. First part, you want to find the velocity of each of them. That's just finding the values or plugging it into the equation. Then you want to find the acceleration. That would be the derivative of these values. And then part C and D specifically are talking about total distance traveled. You're going to need to find the areas underneath the curves or integrate and see what is going on. So try this. If you run into problems, let me know and I can help you. Here's another example of a type of problem that I think would be extremely beneficial for you to try. It's very similar to the one we were just talking about. So go ahead and pause it, try this one, and see what you can come up with. Here's another rate equation where you can use the equation and an integral to figure out what the heck is going on with Fluffy and all of the cat food. So again, one more time, pause it, try it, and see what you can come up with.
Next thing, volume. Remember, we have 3 ways of finding volume. We can either put something down flat and stack a bunch of shapes on top of it, which is what we did with those apples where I said cut it in half and slice it into thin slices and then add up all the areas of that slice. That's what cross-sectional volume is. Or we can have a 2-dimensional shape and we can rotate it around an axis to get a 3-dimensional shape. And we had 2 ways of doing that. One was washer method, where my shape is not touching the axis of rotation. This is real technical with my hands. Or disk method, where it's touching the axis of rotation and I do not have an inner radius. Disk method will have an inner and outer radius. Lies. Washer method will have an inner and outer radius. Disk method will only have a radius that you have to worry about.
We're going to get into these volume equations. Volume of a solid when it's rotated around the line x equals 1, so the line that it's touching right now. Remember, for rotational volume, my axis of symmetry will always be perpendicular, or my radius will always be perpendicular to my axis of symmetry. So I'm perpendicular to the y-axis, so I'm going to need to be dealing in terms of y for this equation. So in this case, I'm going to have 2 different volumes that I'm going to need to calculate. One volume for the top half, because I touched the outside function, that is the rational function, and then one for the natural log function, where I deal with that. Let's deal with the natural log function first. If I want to integrate that, I'm integrating in terms of y, so it's going to be the integral from the 0 y value right here up until this point right here, which I found in my calculator just a minute ago. They intersect at 3.519. 3.519. Now, I want to know the radius, which is the distance from the axis of rotation to the shape. In this case, it's always going to be this distance from here to here, here to here, here to here. So it's going to be the x value of the function, but minus this distance right here, because the x value would be this total distance right here, but I don't want that distance in there. So I need it in terms of x, and I need to get the 1 out of there. So this is going to rearrange. I'm going to rearrange the y equation for ln of x. I can divide by 4 is equal to ln of x. And then I can rearrange this by doing e to both sides. So e to the 1/4 y is equal to x. So the radius that I'm dealing with is e to the 1/4 y minus 1 dy. That represents the volume of the bottom part. Then for the top part, it's going to be the integral from 3.519 all the way up to 6. and it's going to be of the reciprocal function, and I need to rearrange that one. So my reciprocal function is 12x plus 1. I can multiply this across. Y x plus 1 is equal to 12, and then divide across by the y is equal to 12 over y, and x is equal to 12y minus 1. So I can use that distance as my radius minus 1, and I subtract the 1 from that as well, dy. Now conceptually and visually, this is a hard problem. So if I were you, I would go back and look at what I was doing for the x values and the y values and how I switched them, and make sure you truly understand what is going on here. I can definitely see the AP test asking something like this, given how conceptual it is and how you can't just do it with a calculator. I think this would be an excellent candidate for this year's AP test. The last part of this is dealing with cross-sectional volume, and I want perpendicular to the x-axis in this case. So I'm going to be going up and down now, dealing in terms of x. So I know that cross-sectional volume is going to be the integral from the beginning of the base to the end of the base. In this case, the beginning of the base starts at 1, and it ends at this 2.410 business, of the area of the shapes that I stack on top of it. Now in this case, I have an equilateral triangle where the top is sitting on the top function of the natural log, or the 12 over x plus 1, the reciprocal function, and the bottom is on the natural log function, ln of x times 4. The area of that equilateral triangle is root 3 over 4, the side squared. All I have to do to find the side is subtract the top minus the bottom each time. That's how it works. So in this case, it's going to be root 3 over 4. The top is my 12x plus 1 minus 4 ln of x squared dx. This integral could find the volume of the solid by stacking shapes on top of it. This is the area of my shape, and it's the integral from the beginning of the base to the end of the base. If you want some extra practice on volume and conceptualizing what these areas and volumes look like, here's some good problems. I'll move it up in just a minute. Here's some good volume rotations. Here's some good cross-sectional volume problems. And it goes all the way through. And I even have a piecewise function that you could try to find the volume of that one as well. So again, pause it, try some of them. If you have questions, hit me up.
And lastly, let's look at some examples of differential equations. Taking a differential equation, dy over dx, and working backwards and trying to figure out from a rate what the actual function is and how I can apply that in the real world. Here's an example.
Alright, and here is a differential equation. I'll let you pause it, see what's going on with this bacteria in a petri dish. If you want to try part A and B, you can. That is review from derivatives. I'm going to jump to part C, because part C is dealing with the actual solving of the differential equation. I want a particular solution, not the general solution, to this differential equation with the initial condition where at 0 there's 12,000 bacteria. So I have to separate my variables first. I have dA over dt is equal to 3/10 a minus 40. So I'm going to need the a business over here and move the dt over here. So I have dA over, divide this entire thing over, a minus 40 is equal to 3/10 dt. Remember, that's the first step. I have to separate variables. Next, I can integrate. If I integrate this side versus this side, a very small u sub needed, a minus 40. So du is equal to dA. So I have 1 over u, which is natural log. Plug my a back in there. Equal to integral of dt is going to be just t. So I have 3/10 t. Please, please, for the love of everything good, do not forget your integration constant. From there, I can start solving for my initial condition. And you can do it either here or rearrange and do it. It doesn't matter. But I need to figure out what this c value is. So I'm going to plug in ln. A is 12,000 minus 12,000 is equal to 3/10 times 0 plus c. Totally made a boo-boo. This is 40, so this is going to be ln of 1160 is equal to c. So my full equation is ln a minus 40 is equal to 3/10 t plus ln of 1160. All I have to do is find the particular solution for a, so I need to get a all by itself. Well, to get rid of this business, to get rid of a natural log, I'm going to e both sides. So this will become a minus 40 is equal to e 3 over 10 t plus ln of 1600. Not 1600. It's been a lot of math. Oh my god, I did it again. From here, I can actually split this up, and this is what we normally did in class. Remember, e to anything like this is really e 310t times e ln 1160. And the e and the ln cancel each other out. So really, this is a minus 40 is equal to 1160 e 3 over 10 t. And then to get a by itself, I subtract 40. So 1160 e 3/10 t minus 40. It's a big gross equation. You can follow the math and go through there. Remember, when we did this, we have separated these variables. We would have solved here and plugged that in, and we'll get a q value. That is what this value represents, and that's why we did this, so we didn't have to do this sort of backdoor calculation right here. So we did a separation at the beginning, so we got, redo it over here so you can see real quick, a minus 40 is equal to e 3/10 t plus c. We lumped that together, and we said that that e to the c is a q, e 3/10 t, and then we separated it like this. One more time for good luck, and hopefully my camera doesn't crap out the last 2 seconds. I can get the q up here, I can move the 40 over, and this, if I plugged in my initial condition of 0 is equal to 1, 1, 2, 1, 2, 0, 0 is equal to e 3/10 times 0 plus 40. This will cancel out to 1 because e to the 0 is 1. So I'll get 1, 2, 0, 0 is equal to q plus 40. So q is equal to 1160. And it comes out to the exact same thing both times. If you wanted some extra practice on just solving these differential equations, here is a page of solving of what you can do with that. Also remember, we talked about logistic growth differential equation. If you want to practice some of that, here are some more examples where you can go through, solve through some of these. I'll leave it up on the screen for just a hot second. Here's the bottom of that page. And then over here, I would really types of problems like this, full-blown word problem situations where the AP test could throw something at you like this, where you cannot get a ton of help on it unless you know exactly what you're doing. So check out these type of problems and see what you can do.
Nope, not using this one. Now, that is integrals for most of the things that we've talked about in class. Again, this is meant to be a review and spark your brain on thinking about those things. Remember, there are a couple small things in there that we didn't really talk about in this video. Things like average value, 1 over b minus a, integral a to b. Or you can talk about total distance traveled. We touched on that, but not a ton. There are little bits and pieces that you need to remember, also improper integrals, all these smaller things that might show up, but you need to remember them and go back through them on your own. All right, time to pump the brakes. It's story time. You heard my starfish story mid-year. Here's another one of my stories. This was told to me a long time ago, and it's honestly one of my absolute favorite stories to tell. So, here it is. So there was a biologist at the beginning of the century who really loved studying giraffes. And at this point in history, not a lot was known about giraffes. People pretty much knew the biology about it, but no one had exclusively studied giraffes. And so this guy decided one day, okay, I'm going to leave my family, I want to travel to Africa, and I want to be out there in the wild observing giraffes and just see what I can figure out. After about 6 months in the wild of studying all these giraffes, he had found one herd that he really liked. And he couldn't describe it, he couldn't help it, but there was one giraffe in particular that he sort of honed in on and said, yep, this is the one I really want to study. After staying with this group of giraffes, and this giraffe in particular, for about 6 or 7 more months, he noticed something interesting. The giraffe started acting a little bit weird. It would be more seclusive, it wouldn't interact with all the rest of the giraffes, and then he noticed it. The giraffe was pregnant. Now, to observe a pregnant giraffe in the wild, this hadn't been done yet. Yeah, we had giraffes in captivity, but no one had been in the wild and observed this species give birth and go through its maternal cycle other than in captivity. So he was elated. He was so excited. He kept writing letters back to his family saying all the wonderful things he thought he was going to discover, and was just super excited to be in that moment and observe everything. Now, what this scientist didn't know yet, and what we hadn't figured out, is that the normal time for a giraffe to be pregnant is somewhere between 13 and 15 months. So he was out in the field following these giraffes, with certain breaks in there, for almost a full year until the day it finally happened. When the day finally came, the scientist noticed that the giraffe was acting even more weird. It went off all by itself, and while hidden in the brush, he documented all of this. The giraffe stood up on all 4 legs, as tall as it possibly could, and began to give birth. And again, no one had seen this, and so he didn't know what was going on. But instead of getting low and helping the baby out, the giraffe stood real tall, and the first thing this baby giraffe knew, the first sensation of life, was falling from the mom and hitting on the ground. Now the scientist was straight up shook. How can a mother who is supposed to be caring and nurturing just drop its baby on the ground? The first thing it knows, the first breath of life, is pain and suffering. How could this happen? But that's when things went from bad to worse. Being so focused on the giraffe, the scientist did not notice that in the brush around him, a pride of lions had crept up. Sensing an easy meal, they were wanting to attack the mother and the baby and take both of them. Now the baby giraffe had been rolling around on the ground, and it finally started to stand up. It put one leg up, the other leg up, and started to stumble and wobble up. And just as it was getting its balance, the mother's back leg came out and swiped its legs from underneath it. And the scientist had no idea what was going on. Here are these lions. Surely she knew what was going on, and she was knocking her baby down. Maybe there was something wrong with it. Maybe there wasn't something he understood that was going terribly wrong. So again, the baby giraffe started to get up. This time a lot slower. All it's known to this point is falling, hitting, falling, and hitting. And so it starts to get up, it crumbles, it starts to get up, It goes up on one, falls a little bit, up on the other, and finally manages to stand up tall. And again, mom's leg comes, knocks it straight back to the ground for a third time. Now, imagine what the scientist felt. Here is this animal that he has spent now almost 2 years documenting, something he's so passionate about. And here it is, just getting knocked to the ground, and he has no explanation for it. He just wants to scream. He wants to yell out and protect it, but he knows that that's no good for himself or the baby. And so one more time, the baby starts to wiggle up, falls out of exhaustion to the ground, starts to get up, gets all the way up, and one more time, the mom's leg comes to knock it down. But this time, something different happens. Instead of going all the way to the ground, the baby giraffe stumbles and rebounds and gets back up a little bit. The mom's leg comes back again. This time it stumbles even less and stands back up. And one last time, the mom's leg comes back from underneath and the baby giraffe doesn't move. At this point, in this point only, the mom leans down its head, they nuzzle, and they walk off. The lions retreat, and everything is safe. I get it. This is not ideal. It's not ideal for anyone. There's so many excuses that we can make for ourselves of this, and this have gone wrong. But think about it. Up until this point, you have been trained so very well. Everything we as teachers and the world has done to you might seem like it's constantly knocking you down. But trust me, as someone who's been in your position, and definitely not the same position you're in right now, there's a reason for it. You're getting up stronger, you're figuring out how to do this, and whether you acknowledge it or not, you are growing as a person. Each blow that you have been dealt, you've been able to get back from. Whether you've gotten all the way up, or just part of the way up, you've been able to get back. And this is no different. We're gonna be able to get through this. You will get back up. To quote one of my all-time favorite movies, and to be a little trite about it, why do we fall? To learn to pick ourselves back up again. I love you guys so very much. I've said it before, I'll say it again. You are the reason I get up to work with kids every single day. Just because we're in distance doesn't mean that it's changed at all. I believe in you 100%, and I've never been more confident in a class of individuals than I am with you all. You've got this. Take a breath. No matter what happens, I know you'll get back up stronger. We're gonna get through it. Everything's gonna be fine. It's gonna be a great week, and then we'll take a little break. Love you guys. Study, prepare. It'll be fine. Deuces.